Hello students, good evening all. So welcome back to our next session on chapter applications of integrals. Right, so far we have started with our application of integrals where we have discussed our areas under curves, some part of it. So now we are just going to have the continuation part of our applications of integrals. So let's just have a quick overview guys, what and all we have covered so far in our application part. And what in today's focus, like what topics will be our today's focus in our today's session. So that also we are going to have a look here. So if you remember in our previous session, we had a quick discussion of curve tracing and what and all steps involved in it and what and all information we can grasp from the tracing of the curve, like from the plotting of the curve. So that and all we have seen, and corresponding question also we have solved, how to actually for a given curve, how we actually get the information, entire information by the giving, like by taking at the particular graph of our given curve, right? So after our curve tracing, we have discussed area bounded by a curve, right? So in this area bounded by a curve guys, we have discussed a curve. When we take that curve with respect to the x-axis, how the area turns out to be. So that will be our first case where we have seen with respect to the x-axis. So the area bounded between the curve and the x-axis, that will be one case guys. And the second one we have discussed in our previous session is area bounded by the curve and the y-axis. So these are the very basic and typical things which we have covered in our area bounded by a curve. But there is one more part which we are having in this area bounded by a curve, that is the third part, where we are having a curve, which means the curve will be a parametric form. So what happens if we are having a parametric form of it and how we actually find the area bounded by that. So that we are going to discuss today. So today we are going to start with this area bounded by a curve with respect to the parametric form. So that will be our starting concept, starting topic of our today's session of application part of the integrals. Right, so once we have started with that, we are just immediately jumping into the next concept, that is symmetrical area. Right, so maybe you guys have aware of what is this symmetric part. Like if we are having a graph, we will actually say that whether this graph or this plot is symmetric about x-axis or symmetric about y-axis, or else it can be symmetric about the horizon too. So we know that and all. In the same typical manner, we'll be having a plot of area which can be symmetrical. Right. So if you guys remember in our previous session, we had a question related to the parabola as well as the latus rectum. Isn't it? So there how we actually find the area there. So we have directly taken, for instead of the entire area, we have taken 2 times of the half area. What does it mean? The area of these two parts are actually symmetrical. Right. So that will be called to be an symmetrical area. So that we'll just have a quick discussion over it, and then we'll just start doing questions related to the symmetrical area. And coming to the next part, we'll be having positive and negative areas. So can you guys tell me, if I say something like positive and negative area, what will be the first point which will be striking in your mind? Any idea? So my question is there any possibility that an area can be negative? So is it any possibility that the area of any plot can be negative? Can anyone give me the answer? If it is, what does it actually meant by? What does actually a negative area meant by? So if we take our coordinate axis, right? So here we'll be having positive y-axis. This will be our negative y. Similarly, this is positive x and this will be the negative x, right? So for any plot, we cannot actually have the area negative. So what does it mean actually is, it will be in the negative part of the coordinate system. So if we have an area somewhere like this, so there is a possibility, so this area will be, if we find out the area, for example, so this is 2 units and this is minus 2 units. So how you will be finding 2 into 2? So square 2 into minus 2, it will be 4. If it's a square. But as here it's minus 2. But in general, how we actually calculate, we'll take the units. So what are the units of this side? So this will be 2 and this will be 2, which means the area will be 4 units only. But instead it will be a negative area because it's in our quadrant 4. So likewise, we'll be having a negative and positive area. So that also we'll be seeing and we'll be looking into the examples also. So far what we have discussed, we are actually doing the area bounded by a, exactly. So many of you has already given. So negative area means it will be in our negative axis, that means below axis. So yeah, so far what we are counting here, we are dealing with the curve with respect to x-axis, with respect to y-axis. But now after that, the next part we are having is finding the area between two curves. Right, so here instead of one curve and x-axis, one curve and y-axis, we will be having two different curves. And we have to find the area bounded between these two curves. So that will be our next concept after this, which we are going to start. Right. So these are the concepts, guys, which we are going to look into our today's session of applications of integrals. So let's get started with the first one, which is the parametric form. Right. So area of a curve in parametric form. So what actually a parametric form meant actually here? So we will be having in another variable. So in general, our curve will be whether in terms of x variable or in terms of y. But here we will be having our x also in terms of a variable. Similarly, y also in terms of a variable. Right. So which means our x will be equal to f of t and y will be equal to g of t. So these are two parametric form. Right. So then the area bounded by the curve with x-axis. If we want to find with x-axis, how we will be trying to find? So it's obvious that we have to get the function in terms of t. Right. That means we will be finding it. That is nothing but integration from the limits t2 to t1 and the function will be g of t and the differentiation of f dash t dt. So this is the formula which we will be using to find the area of a curve in a parametric form. So this is the general formula, general format or formula which we can say here, which means our function should be entirely in terms of the t variable. As we are dealing with the t variable, the limits should also be in terms of t. Right. So this is the formula which we'll be using to find the area of a curve in a parametric form. So it's like the similar thing. Right. So let's, you'll be getting easier understanding when we deal with a question. So let's solve a question here, guys. So find the area bounded by the curve x equal to a cos t, y equal to b sin t in the first quadrant. So can you guys tell me how we actually find? So first, let us find out the function first. So please tell me the function, guys. What will be the function here first? So here what is our x? X will be equal to a cos t and y will be equal to b cos t. So if we take both of these x and y, so what will be our equation in terms of parametric form? So this will be nothing but equation of parametric form of equation of a ellipse. Yes or no? So what will it be? So x square by a square plus y square by b square will be equal to 1. So if you substitute and check your x and y, so this will be the curve of an ellipse. Yes or no? So as it's in a first quadrant, it will be starting from 0, right? And it will be going until the first variable a, right? So the limit will be integration from 0 to a, and the function will be g of t into f dash t. So what is g of t here? That is our y function, which is y, that is b sin t, and the differentiation of x. So differentiation of x will be, so cos t differentiation will be minus sin t, so minus a sin t, and it's obvious that dt will be here, right? But here our limits are 0 and y in terms of normal function. Now we have to convert this into our t function, right? So let's substitute 0 and see what will be our limits. So here if we substitute 0, so t will be cos 0, when cos will be 0 at pi by 2. So this is the term which we are taking because these are our x limits 0 to a. So let us substitute in x 0 and check what will be the t1, t2. So if I substitute x 0, I end up having cos 0, that will be at t value pi by 2. Similarly, if I take cos x a will get cancelled and I will be having cos t1. So when will be cos t1? It will be at angle 0. So now instead of I am having a 0 to a, so my 0 to a are nothing but my limits for the x variable. Yes or no? So here, as I am taking my function here in terms of x, so let's see if somebody has given the answer. Okay, not it. So let me explain you clearly this part. So in general, so this is first quadrant, so it's obvious that it will be starting 0. As I am taking to x-axis, so as I am taking the limits of the x-axis, so the x-axis related coefficient will be a. So my limits will be 0 to a. And here what should be my function? My function should also be in variable x. So let me take it y of y dx. So this y also I have to write in terms of x because my limits are related to my x-axis. But here if you observe, the given functions are of parametric form, which means my limits also have to turn into my parametric form. Similarly, my function also. So let's convert the function first. So if I convert my function, it will be y function, that is b sin t, into the differentiation of x function, which is minus a sin t. Right guys? So now initially our limits are 0 and a. So these 0 to a are my x limit. Here what is my x? X is equal to a cos t. So let us substitute these x values here so that we can get the corresponding limits for our t variable. So if I substitute 0 here, it will be 0 a cos t. That means cos t will be 0. So when cos t angle will be 0, when t equal to pi by 2. So here my limit turns out to be pi by 2. So the next here my x value is equal to 8. So let's substitute the x value equal to a. So a equal to a cos t. That means cos t equal to 1. That will be at cos equal to 0. So now my limits are also turned in terms of t, where my function now has been turned out to be integration of pi by 2 to 0 minus ab, we can pull that out. So minus ab sine square t dt. So this is our function now which we are remained with. Right. So as AB also a negative, what can we take? AB also a constant. We can actually pull that out. So which will be integration. So minus AB integration of sine square t dt with the limits pi by 2 to 0. So can you guys quickly find out the integration, definite integration of this function and get me the answer? I'm just erasing this part. So we have remained with minus AB sine square t dt pi by 2 to 0. So now what I'll do, I'll just interchange this limit so that I can change my sign here. So now it will be AB integration from 0 to pi by 2 sine square t. So did you guys remember something related to our Wallis formula right now? Right, so it is something related to our Wallis formula, guys. So that's why I have changed the sign so that I can exchange my limits here. So apply your Wallis formula which we have learned earlier. So for applying the Wallis formula, the limit should be 0 to pi by 2 exactly, and the function should be either cos or sine, and the power can be even or odd. So here it is even, so it will be AB into 2 minus 1, and then it will be 2 into, so next one will be 2 minus 2, as it's a 0 we won't be going that far. So and then here it's a even, so we have to multiply with pi by 2. Right, so now 2 minus 1 will be 1, that means pi AB in the numerator, so 2 into 2 will be 4 in the denominator. So the integration, that means the area bounded by this parametric curve is given to be pi AB by 4. So this will be the area, pi AB by 4 square units. So I hope you guys got an idea here how to deal with this type of parametric form of function. So let me check any doubts. Not it. Okay. So the only thing while dealing with this parametric form we have to do is the changing of the limits, guys. So when we are taking x, if the function is in terms of x variable, the limits also should be related to the x coordinate. If the function is in terms of y variable, the limits should be related to the y. If the function is in some other variable, the limits can also correspondingly has to be changed in that corresponding variable. So that's what we have done it here, and the final answer here which we are getting is pi AB by 4. Right, so let's move on to the next one, guys. So here comes one more question. So can you guys quickly solve this question and let me know what is the area bounded by this region? So it's a random question. I won't say it is related to parametric form, but yeah, it's a random question related to area bounded by the curve. So quickly solve it and let me know the answer. So first thing, you have to plot the curve, plot the graph of it. So what are the curves which are given here? So the curve is x square equal to y, and the another one is line y equal to 4. Plot the curve as well as the line on the graph and see what will be the required area here. Quickly guys, if anyone finished it, you can let me know the answer. So what is the first curve? It's obvious that it is a parabola. So as it's x square equal to y, the parabola will be like this. Yes or no? X square equal to y and y equal to 4. So if we are having somewhere here y equal to 4, so that line will be something like this. So y equal to 4 guys. So your required area, that is your area bounded by these two lines. So curve and line will be this shaded portion here. So now how we will be finding the area, required area here. So this is the point 0, 0 and this is 0, 4. So if I check this part, so let me take this part 1 and part 2. If you observe here, these two areas are same or not, part 1 and part 2, which means those two are symmetrical areas. If we find one of the area, we can multiply it by 2, we can twice it, and that will be the final area. Right. So if we take the part 1, what is the area that is required here? So this is the curve which is varying the, we don't know exactly the x coordinate here. But we know that whatever the x will be, we know the y coordinate, that is 4. Yes or no? Right. So now we cannot go with the x, but instead we can go with y. Yes or no? Right. So now my y variable varies from 0 to 4 for this first curve. So my required area will be 2 times, because I am just dealing with the part 1. So if I have to find the entire area, so it will be obviously twice of it. So twice of it. So my y variable will be varying from 0 to 4 for the curve. So here, as we have taken the y coordinates, our function should also be in terms of y. That means x square is equal to y. That means x will be equal to root over y. That means here the function will be root over y. So you have to find the area, that is required area here will be twice of integration 0 to 4 y power 1 by 2 dy. So quickly find the area guys here. Come on. So I'll just give you time so that you can just work it on and let me know the answer. So what you have to do, you have to simply apply your basic integrals which we have seen, formula for it, and simply find the value of this definite integration. So did anyone got the answer guys? The area? Okay, Shivaranjani has given the answer. Perfect. So let's see for a few more. Okay, Arun also given the answer 32 by 3. Perfect. So here how we'll be doing? So the integration here will be 2 times of 2 by 3 y power 3 by 2 0 to 4. Right, so we have to substitute. So here it will be 4 by 3 into, we have to substitute 4, that is 4 power 3 by 2. Anyways, no need to substitute the 0, it will become 0. So 4 can be written as 2 square, where 2 will get cancelled. That means 4 into 2 cube by 3, that is 4 into 8 by 3. Sorry, 4 into 8 by 3, that is 32 by 3. So the area here, the required area or the area bounded by this region is 32 by 3 square units. I hope you guys got it. So Arun and Shivaranjani has already given the answer. So if anyone has any questions in this, you can let me know, or else we can just move ahead with our next concept. So let's move on, guys. So here comes the symmetrical area. So just now we have dealt question related to that. So if the curve is symmetrical about a line or horizon, then we can find the area of one symmetrical portion and multiply it by the number of symmetrical portions to get the required area. So we can see, for example, just now we have dealt with that kind of question. So here this is portion 1, this is portion 2. So these two are symmetrical here. So both the areas will be symmetrical here about this axis. That means we can actually multiply it by 2. So if I have a curve something like this, guys, where here this is the required area if we want to find. So I am noting them to be 1, 2, 3 and 4 parts. So by looking at here, we can say all these are symmetrical, all the areas are. So if I could find one area, I can multiply it by 4 because I am having 4 similar areas. So this is the easiest way when we have symmetrical about any line or horizon, symmetrical area. It's easy that we can find one symmetrical portion and we can multiply the number of symmetrical portion which we have there to get our required area. Right, so let's deal and do one question related to the symmetrical area now, guys. So let's do it. So if you guys remember, we had same type of question already. We have already solved same type of question, same model. So I hope you guys can solve it quickly and let me know the area, required area. So here if you look at it, the question, they have given a parabola and you have to find the area bounded by this parabola as well as its latest rectum. So let's see, did anyone given the answer or not? Not it. So let's see. Let's wait for a few more minutes. So first and foremost thing, as usual, you have to plot the graph, guys. You have to plot the graph. Then only you will be identifying what and all limits you have to take, what is the curve you have to take. So that's the whole idea here. Make it quick, guys. Make it quick. Meanwhile, if you face any doubts, any queries, please let me know. So, okay. Anyone got the answer, guys? Not it. So what is the graph of our parabola? So the parabola which is given is y square equal to 4x. So the plot will be something like this. Right. So this is origin. We can state that. And what about the focus here? The focus value will be a comma 0. That means here a value is 1 because our general form of equation of parabola will be 4ax. By comparing both of them, we can predict the value a equal to 1. So the focus will be 1 comma 0. So you guys are sure that the lattice rectum will be passing through the focus, which means okay. So this will be our required portion of area. So my figure is something. So let me draw it again. One comma 0, 0 comma 0. So this is our required area, guys. Where you can see this is part 1 and this is part 2. So these two areas are symmetrical because this point and this point will be plus or minus difference. So they will be same. So the only thing we can say here is these two parts are symmetrical to each other. Okay, Siddharth given the answer. Perfect. Let's see if anyone get the same answer or not. So let's check whether Siddharth's answer is correct or not. So let's see for one or two more answers, guys. So this is part 1 and part 2. So here For this curve, you know the y values here, or else you can take the x values. So y is anyway 0, but the x is varying here. That is from 0 to 1. Right. So integration of limit 0 to 1. As I have taken my x coordinates of the curve, I have to write my function in terms of x. That will be root over 4x dx. So this is my area of only one part. But here I am having two parts. So both are symmetrical. I can make it to be twice of it. Yes or no? So now my integration turns out to be 2 times integration of 0 to 1 2 root x dx. That will be my required area. So 4, 2 into 2, 4. So it will be 0 to 1 x power 1 by 2 dx. So quickly do the differentiation, guys, and let me know what's the answer. Okay, Arun, Shivaranjani and Siddharth already done it. So we can do it easily. So same thing, 2 by 3 x power 3 by 2, and the limits are 0 to 1. So here it will be 8 by 3. So if we substitute 1, anything power 1 will be 1. If we substitute 0, it will be 0. So 1 minus 0, it will be 1, which is nothing but equal to 8 by 3 square units. So here the required area, which is bounded by the parabola y square equal to 4x, and its lattice rectum is given by 8 by 3 square units. Right, guys? So let's move on. So just now we have seen our symmetrical area. So now let's see the positive and negative area. Right. So the area of a plane figure is always taken to be positive. Right. So if some part of the area lies above x-axis and some part lies below the x-axis, then the area of two parts should be calculated separately and then they have to be added. Right. So if we are having one above the x-axis and one below the x-axis, so one will be negative and one will be positive. So we have to do the calculation separately and then we have to add it. If not, there might be some calculation mistake will be happen, because according to the negative axis, some will be below the axis, some will be above the axis. So it is preferable that we have to do the area of the two parts separately and then add the numerical values. So here you can see. So here these two are symmetrical. We can say that. Right, but one is above, sorry, these are not symmetrical. One is above the axis and one is below the axis. And here it is x equal to b. Here the x value is x equal to b. And here the x value is x equal to. So this is x equal to a and this is x equal to b. Right. So as one is above x-axis and the other is below x-axis, so we have to separately find the areas of these two and then we have to find the combined area. Right. So here if the curve crosses the x-axis at C, so here you can see at C it is crossing, then the area bounded by the curve y equal to f of x and the coordinates here x equal to a and x equal to b. By the figure itself you can directly say that b is obviously greater than a. So then our required area will be, so this is limits are from, so here to here, so here from x to c first part. Right, so that means limits are a to c. So limits are a to c and the function f of x dx. So whereas here the limits are c to b f of x dx. So here it is in positive area. So if we take the modulus, it will be the positive. Here it will be the negative. Right, so you can take the modulus here because even the negative area should be taken positive and then you have to add the entire area, which will end up giving you the final required area of the plot which we have to find out. Right, so let's see an example, guys, with respect to this type of negative and positive axis, and let's see how we can get the answer. So let's try and simplify it. So for any curve, for anything, what is our first step? Try and plot the graph here. Here if you observe, they have given the curve to be y equal to cos x, but here they have given the interval 2. So you have to take that interval area only. So that will be our required portion. So plot the graph of y equal to cos x and then take the area in between the interval pi by 4 and pi. But whenever you are finding the areas, you have to take the modulus of it. So after plotting it, can anyone tell me what are the limits you are getting? Because by looking at the plot, the graph which you are plotting, you can get an idea of what will be the limits. So if you guys plot the graph of it, can you please let me know the limits, what you are getting here? Like you have seen here, what are the A, B and C values? So let's plot the graph, guys, and let me know the limits so that I can just verify you to proceed further. So let's see, did anyone given the limits? So have you guys plotted the graph? Quickly let me know, guys. So we are learning how to, how will be our graph of cos x since our 11th standard, where we have learned our trigonometric equations, trigonometric functions and identities. So this will be when x is 0, but here we required when x is pi by 4. So, and I'm taking pi by 2 as a middle point, as we know it's easy. And I'm taking here pi. So when cos pi by 4, what will be the angle value of it? It is 1 by root 2, right? So the graph will be somewhere here. It will be coming like this. So whenever value is pi by 2, it will become 0. That means if I plot it like this, so here I will be having the point. And I will be having my graph something like this. But I have to find till pi only. So I'm just dropping it here. And similarly here I have to find in between pi by 4. I'm dropping it here. So my required area will be This part above x-axis and this part below x-axis. So 2 parts we are having. So now how you guys are going to find the area bounded by this curve of y equal to cos x as well as x-axis? I didn't get any answer yet. Okay, so let's wait for a few more minutes. So as I have given you the graph, you might have get an idea how to get the area between the curve y equal to cos x and the x-axis within the given interval of pi by 4 less than x less than pi. Okay, Siddharth has given some answer. So as we know that, so this is above x-axis and this is below axis, you can find as 2 separate parts. So first you can find the part 1 area and then you can find the part 2 area. So what will be your part 1 area? So that will be integration. So what are the limits here from pi by 4 to pi by 2? And that is your, which axis points are they? So those are x-axis points. So your function should be in terms of x, which means cos x dx. What is integration of cos x? So integration of cos x will be sin x. So sin x within the limits pi by 2 and pi by 4 here. So sin pi by 2, it will be 1 minus sin pi by 4, it will be 1 by root 2. So this is our first part area, guys, 1 minus 1 by root 2. So similarly, can you guys find the second part area and let me know? So second part area will be integration from the limit pi by 2 to pi cos x dx. So here it will be again sin x and the limits are pi by 2 to pi. Right. So here we'll be having pi, that is sin pi. So we know that this is the negative area. So for negative area, what we have to take? We have to take the modulus here. Right. So sin pi, that is 1 minus sin pi by 2 will be, sin pi will be 0 and sin pi by 2 will be 1. Right. So modulus here, it will be 1. So now we are having 1 minus 1 by root 2 plus 1, which means 2 minus 1 by root 2. So if we simplify it, it will be 2 root 2 minus 1 by root 2 will be our final area. So why it will be the final area? Whenever we will be having the area in the negative side, we have to take the modulus of it. So that's what we have seen in our previous slide, where we are discussing our positive and negative area. So now if we take the modulus of second part, it will become 1. So our first part area is came out to be 1 minus 1 by root 2. We have to add our second part area, which is 1. So here it is 2 minus 1 by root 2. So if we take the LCM, it will be root 2. So 2 root 2 minus 1 by root 2 square units will be the area which is bounded by the curve y equal to cos x and the x-axis within the given interval pi by 4 less than x less than pi. So yeah, so if we simplify it by taking the root 2 value, you end up having in decimals, that is 1.293 square units. So some of you has given in that point of view in decimals. So anything is fine. So I hope you guys got this point also. So let's move ahead. So here comes one more question, guys. So using integration, find the area of the triangle ABC whose vertices are given ABC. So you guys are aware of when you are having a triangle coordinates, you know how to find the area. So you'll be using simply the formula of root over s into s minus a into s minus b into s minus c. But instead, here I have mentioned you have to use the method of our integration to find the area. So can you guys give it a try how you'll be finding using the integration method here to get the area of a triangle ABC? It's a bit lengthy, I can say, but yeah, we can try half now. So if time runs out, we can take it as homework and we'll do it for tomorrow, next session. But yeah, you can start solving it now. So first, the thing you have to get into your mind is how to begin it, how to start the thing here. So using integration in the sense, the first thing you should get is the figure of this triangle and the equations of the line, right? Because without the equations of line, you cannot do the integration part of it. So first thing, plot the points, plot the graph, and then see the equations of those sides of the triangle. So that will be the hint which I am giving here. Start with that, start solving with that. If once we could get a clear vision of the figure of the diagram which we required, then it will be very, very easy to find the area bounded by that region or else our required area. Okay, someone has already given the area. Okay, fine. So you can get the area by our normal method easily, but here my point is to try solving and find the area using the integration method. First, let's try and plot the graph here. So let me take the thing. So first one, 4, 1. So somewhere here. And next one, 6, 6. So 4, 6 here and somewhere here 6. So let me take it here. So this is 4, 1 and this is 6, 6. And the next one is 8, 4. So 6, 7, 8. So somewhere here. So 8, 4. So let's just join this triangle. So this is our required area, guys, of this triangle. But with using our integration method, we should be aware of the equations. So let me prolong this. So this here x equal to 4, here x equal to 6, and here x is equal to 8. Right. So now the next step here, which you will be doing here, finding the equations of line. So this is A, this is B, and this is C. So as you are having points, you know how to find the equation of lines. So find the equation of line AB, find the equation of line BC, and find the equation of line AC. So if once you got the equation of lines, okay, Siddharth has given, okay, Arun, okay, most of you has given the answer, no issue, okay, fine, Siddharth, used integrals only, okay, good. So here I am just for others, for reference, I just drawn the figure also, and similarly, I'll just give you the equations of the sides also. So it's easy when we have 2 points, how to find the equation of line. So here it will be y equal to 5x by 2 minus 9, that is my equation of line AB, and my equation of line AC will be y equal to 3x by 4 minus 2. Similarly, my equation of line BC is given by y equal to minus x plus 12. Right. So as we have our line equations as well as the integration coordinates, so how we will be finding? So our required area using integration will be, right, so integration from what and all the points here, from x varying from, so this is the first line which is varying from, what are the limits here, 4 to 6. So what is this line? Line AB, that means 5x by 2 minus 9 dx. So plus, and the next is varying from 6 to 8. Right. So here, if we are finding this entire thing, it actually includes this part also. So that we have to eliminate at the end. Right. If I included my area of this line, this means here what I have included, the entire area of, let me take A, B, C, D, E, F, these points. So here what does it mean? Integration from 4 to 6, 5x by 2 minus 9. So it includes this entire area of A, B, O, E. So here similarly from 6 to 8, in the sense, what is the line? That is line BC. So minus x plus 12 dx. So this includes entire area of E, B, C, F. But I actually required only the area of ABC, which means I have to eliminate this area of trapezium OA, C, E, sorry, CF. So that is which line it is going from 4 to 6, the line AC. That means minus of limits 4 to 8, and the function here will be 3x by 4 minus 2 dx. So that's it. Right. So if we could write this, the next thing is simply the integration here, and you end up getting your final answer. And the final answer, the area is given by 7 square units. So I hope most of you has already done using the integral methods. Very good, guys. So that's all for today. In our today's session, we have started with area bounded by the curve, and we have dealt with our positive and negative area, as well as we have done our symmetrical area questions, and we have even seen the finding the area of a triangle using our integration method. So in our next session, we are going to start our finding area between any two curves. So that's all for today, guys. If you are having any questions, any doubts, you can text me, you can let me know. Right, and we can have a discussion and we'll just clear out your doubts. So that's all for today. So yeah, this question most of you got it. Good, guys. So we'll just continue the rest of this application part in our next session. Thank you.